Hello, everyone. Today we have Kent Kasper joining us from Climate Reality Leadership, an organization which purpose is to educate folks on climate change and its causes and effects. Kent's interest in climate change is due to his enjoyment for winter sports. As a ski instructor, he's really passionate about getting out and partaking in winter sports and is worried about how climate change would affect and impact those going forward in the future, and has noticed over the years changes already in the season. So welcome, Kent. It's great to see you. Great to have you here today. Welcome.
Thanks, Chad. I really appreciate it. Again, thank you very much for the opportunity to come talk to you at the library. I'm excited about it. I want to talk to you about climate change. As Chad said, I think this is something that we really, particularly at this point in time, should lean into. We see this more and more in our nightly news as some of the things that scientists have said for years and decades are really coming to pass. If we simply turn on our news, we're beginning to see these. So what I want to do today is talk and take a big, deep dive into climate change. I want to talk about the facts, the science, the evidence. I also want to talk about some of the solutions. The solutions are here. What we really need to do is implement the skill that we have and find the will, particularly I think the political will to go ahead and move this ball forward. The other thing I want to talk about is the good things that are going on. There are a number of good positive indications in terms of the changes we're making. So I want to talk about that, but I also want to finally leave you with the idea that there's a lot more work to do. And I think that there's some things that we can do as individuals to kind of move this ball forward. And I also want to say that I think it's important in terms of time. What we do, this kind of wait and see behavior that we've engaged in for so long is something that I think we need to kind of move away from. So with that, as Chad said in the beginning, my interest in climate change comes from my interest in these outdoor winter recreational spaces in particular. And I've been a skier and have really grown up here in the state of Michigan. And what I would have you say that this winter recreational space is beginning to evolve. It's beginning to change. And so before I dive into this bigger conversation of what's happening here in our climate, I want to talk about what I see here in the state of Michigan within that winter recreational space and what's beginning to happen. So I've listed a few things here, and I want to cover these really quickly before, again, I go into that bigger piece. So first of all, what I've indicated here is reduced snowpack here in our state across the entire season. This is simply borne out by the science. And what I can tell you, we have a saying in skiing, and that saying goes that if there's no snow in people's backyard, they're simply not thinking about skiing. This is true. We see this impact not just the perception of skiers and how available it is, but obviously the quality of skiing as more resorts are having to depend upon those kinds of machines to create the conditions that we need to ski here in our state. The other thing is shorter winters. This is really true. Our season now is kind of ending very abruptly, oftentimes in the early winter season, late winter season. I can tell you that my season here in Michigan is no longer, in terms of my actual ski instruction, of about 10 to 12 weeks in length. And what I typically tend to see is winter ending very abruptly. I would have thought that this season would have ended about mid-March. But in fact, after 3 particularly warm days, the season came to an abrupt halt. And this happens more often than not these days. The other thing I would mention is when those conditions occur, the conditions at the ski hill become very unsafe very rapidly. And as a result, oftentimes things are brought to a very abrupt halt. One of the other things I want to mention, as I'm sure that people have seen, is there's more overall precipitation that falls as rain, really, instead of snow. And this, too, obviously impacts and degrades and erodes those conditions at a ski hill and can make those conditions very unsafe and bring the winter season to an abrupt halt. What these first 3 primary reasons or examples do is they kind of create the second 2. And the second 2 leads to the fact that we just have fewer visitors and revenues overall over time. The season is shortening. The quality of that season is a little bit suspect. And that also impacts the quality of those jobs within that kind of winter recreational industry and that winter recreational space, right? They're just a little bit less dependable than before. And so why is this important? Why should people in the state of Michigan find this of value and significant? First of all, here, what I've indicated is that winter tourism in the state of Michigan really is the jobs that it creates are significant, right? Roughly about 9,500 jobs in the state are created from winter tourism. That's skiing and snowboarding, but it's also things like cross-country skiing. It could be things like ice fishing and snowmobiling. All those things are part of that Michigan winter tourism sector. The other thing that this winter tourism adds or is responsible for adding roughly about $570 million to the Michigan economy. So there's a lot of reasons to be very kind of alarmed by the changes that we see within this winter recreational space. With that, let me go ahead and turn and talk to this larger conversation about climate change and talk about the things that are really beginning to occur. So I want to start out with this photo here. This photo is referred to as the Big Blue Marble. It was a photo taken back in the 1970s by the Apollo 17 mission. And it's really transformative because for those who see our planet actually from outer space, they have a way of describing it as though the borders of our countries, of our states kind of evaporate. And you see our planet as this worldwide collective community. And it also gives you that perspective that the things that we do here impact us all. And that's particularly important as it becomes or as it pertains to climate change. So now what I want to do is we kind of explore this next bit of the conversation. I want to ask and put to everyone three primary questions. And that's really, must we change? Can we change? And ultimately, will we change? So let's do first things first, and let's look at must we change? So oftentimes we step outside our front doors, we may look out into space, and we think that piece of space is just never ending and it goes forever. And if we're looking up into that atmosphere, we think it too goes forever. In reality, what we see here is a shot from the International Space Station of our atmosphere. And you can see our atmosphere is actually a very thin shell, and it acts to protect our planet from what are the worst and most damaging rays of the sun. What we see here are the two layers of the troposphere and the stratosphere. So in order to really describe how our atmosphere is relevant, I want to focus on the planetary system here. And let's take a look first at Earth and the sun. We'll look at Venus. Now we see Mars, and I want to take a look at the atmospheres of each of these planets, right? What we see here is a very fine atmosphere on Mars, very actually somewhat larger atmosphere here on Earth, and then a very large and pronounced atmosphere on Venus. We can see here the average temperatures of each of these planets. So Mars has an average temperature of minus 85 degrees Fahrenheit. Earth has a much more comfortable positive 59 degrees Fahrenheit, and Venus has an uninhabitable 860 degrees Fahrenheit temperature. So when we really dig into this and we ask the questions, why would this be? Certainly proximity to the sun is a key role in this, or is a key factor. We know that this truly isn't the case because if we look at the planet Mercury, what we see here in the planet Mercury is a full 500 degrees cooler than is Venus. So this is particularly relevant. And what we have to do, and the reasons that we recognize are those that really impact that uninhabitable temperature here on Venus, is the greenhouse gases that exist within that atmosphere, right? That atmosphere is comprised of things like carbon, nitrous oxide, and all of these gases act to trap the sun's light and heat energy, and they trap it within that atmosphere. And as this atmosphere prohibits the escaping of this heat energy, it makes it so that it heats that planet overall, once again, to that uninhabitable 860 degrees Fahrenheit. So why is that relevant, really? Why is all of that atmospheric heating important as it pertains to Earth? It's particularly important because we are spewing 162 million tons of man-made global warming pollution into the thin shell of our atmosphere every 24 hours. Now, I want to discuss some basic climate science, and this is not new. This is science that we have understood since the 1800s. What we see here is the sun's solar radiation in the form of light waves kind of passes through our atmosphere. Most of that radiation really is absorbed here by the Earth itself, and it warms our Earth. That's about 50% of that radiation is absorbed by the Earth itself. We see here some of that energy is radiated back out into space by the Earth itself in the form of infrared rays. That is a little over 30%. And then some of that outgoing infrared radiation is trapped by the Earth's atmosphere, and it again warms our Earth. That's roughly somewhere in the middle 20%. So none of this is concerning at this point. Where this becomes a little bit difficult is where we kind of increase those CO2 concentrations within the atmosphere. And as we do that, we trap more of that infrared radiation and we warm our planet further. So I want to illustrate this point because I think it's really important to kind of give you an idea of what this additional heating, this additional warming that takes place in our atmosphere, what this is the equivalent to. So if we look at this here, it says the energy trapped by man-made global warming pollution is now equivalent to exploding 600,000 first-generation atomic bombs per day, 365 days per year. Once again, this gives you the stated example. What I want you to see, and I want to illustrate this for you so you see what this actually looks like. So once again, what I want everybody to imagine that we're doing this 600,000 times per day, 365 days per year. That is the equivalent in terms of the amount of additional heating that we are now absorbing into our atmosphere. So what I quickly want to do is kind of explain how all of this additional warming is impacting our planet in terms of its temperature. And I want to use this example to do that. So what we see here, we're going to focus on the Northern Hemisphere in the summertime. And we're going to use the period from 1951 to 1980 to illustrate how temperature is moving from generation to generation. So if we look at our chart here, what we see is, first of all, a red zone. And the red zone is the warmer than average zone. It depicts temperatures of roughly a half degree warmer to roughly about 3 or 4 degrees warmer. We also see a white zone. This is the average zone. This is temperatures of plus or minus about a half a degree. And then finally, we see the cooler than average zone. This is represented in blue. And this is temperatures of minus about a half a degree to temperatures of minus around 3 degrees or minus 4 degrees in temperature. And the higher these zones occur on the map, the more frequently they occur. So what we're going to do to illustrate this point is we're going to use this time frame as our baseline or our benchmark. So again, 1951 to 1980, and we're going to draw a line around this to give us an idea of how temperatures are beginning to move over time. So let's now take a look at the time of the 90s, right? 1990 to 2000. First of all, what do we notice? We notice there's this entirely new zone that's represented here. It's represented in maroon or crimson, and it's the extremely hot zone, right? These temperatures fall somewhere between 3 degrees warmer and 5 or 6 degrees warmer in temperature. We look at the warmer than average zone, again in red, and what we see is this zone is the largest zone throughout all of the zones. And then we look at the white zone, the average zone, and the cooler than average zone in blue. And what we notice is those zones, within those zones, these temperatures occur less frequently. And we know this because they actually don't appear as high up on the map as they once did. And we compare this to that green outline, that baseline, and we can see how temperatures are beginning to evolve and skew warmer over time. Now let's take a look at this last decade. This last decade was 2010 to 2020. What we see there in that crimson zone, that red zone, right, or that crimson zone, extremely hot. What we see is that zone expands exponentially. We also see the warmer than average zone. That red zone is the largest of all the zones. And we see the average zone in white and the cooler than average zone in blue. These zones, right, occur very infrequently. We know this because they don't fall very high up on our map. And if we compare this to the baseline, right, we compare that to that outline, that green outline, we see how temperatures are skewing warmer over time. What we now know, if we look at that extremely hot zone, the extreme temperatures, right, these extreme temperature events used to occur on 0.1% of land. They now occur on 22.1% of land. This is a full 22% greater than before. So why do we think this is really happening? Well, really the reasons are very simple. We're simply burning more fossil fuels. We're putting this fossil fuel pollution into our atmosphere. And as a result, our planet is warming. What we see here around the industrial period or slightly after World War II, we see how we're exponentially growing the amount of pollutions from fossil fuels. We're really beginning to grow these and put more and more into our atmosphere. If you can actually take a look at the very top of this graph on the far right, you can see where it dips down just a fraction. And this is because we're actually beginning to utilize some forms of sustainable energy like wind and solar energy. Now I want to talk about what exists or what kinds of gases exist within those greenhouse gases, because it's more than just carbon as a result of burning fossil fuels. So let's talk about those very quickly. So first of all, 2% of those gases are what we call F gases. And F gases can come from simple things like processes insofar as refrigeration. They can also come from air conditioners. We can see 5% of these gases are nitrous oxide, right? And nitrous oxide can come from things like farming processes, and it can also come from industrial processes. Then we see CH4. This is 18%. And CH4 or methane really can come from a number of things. It can come from, say, industrial or domesticated animals. It can also come from a variety of farming processes. It can come from uncapped or leaky gas wells. It can even come from the melting of permafrost, throughout our planet. Then what we see is carbon, right? CO2. So that's 7% of that, which comes from land use and forestry. But if we look down at the brown area in the bottom, right, a full 68% is CO2 or carbon from the burning of fossil fuels. So this is by far the largest contributor of all these greenhouse gases. Now, what I want to talk about is the fact that oftentimes people will indicate that these kinds of rises in CO2 levels are cyclical, that these things have changed over time, and there is some truth to that. But we do have to recognize the fact that currently, atmospheric CO2 levels are higher than at any time in the last 800 years, and levels are increasing faster than at any time in millions of years. What we see on this graph here, or this chart, as we look over the last 800,000 years, we see carbon amounts increase and decrease over time. But by the time we get to 1930, right, we blow past prior levels and targets, right? We never really had achieved anything above about 300 parts per million until we get to 1950. And at that point, we blow through that number. And by 2019, we get to levels somewhere greater than 400 parts per million. So let's talk about some of the changes we're beginning to see as a result of adding all these additional greenhouse gases in our atmosphere. First of all, what we see is all of this additional warming, particularly in terms of surface temperature. We're beginning to see surface temperatures depart quite a bit from their average temperature. We look at this chart taken all the way back in 1880, all the way up to today in 2020. We can begin to see these temperatures rise over time. And in fact, they begin to rise exponentially, warmer year after year, all the way to 2020. We now know that 19 of the 20 hottest years on record have occurred since the year 2002. And the hottest years in recorded history have been the last 7 years. Now, I want to explain temperature a bit, and I want to use this model to do it, to give us an idea of where we stand, where our goals are, and where we'll actually end up if we do nothing. So we're currently, you can see here at about 2020. If you look at the blue and black line, you can see that we've increased our temperature by about 1 degree Celsius. You can see here, if you look at the dotted red lines, right? Our objectives, our goals and targets are that we do not want to achieve any more warming than 2 degrees Celsius. And in a perfect world, if we really are aggressive, we would prefer to be right about 1.5 degrees Celsius of warming. What we see under current conditions is that we will blow through 1.5 degrees Celsius of warming right around 2030 and above. And by the time we get to 2050, we blow through 2 degrees Celsius of warming under current conditions. But if we do nothing under our current conditions, by the time we get to the end of the century, so 2100, we could experience roughly 3.6 degrees Celsius of warming, which is the equivalent of 6.5 degrees Fahrenheit of warming. And I want to explain and show you some examples of what this could look like. Now, these are but a few, but if we would see 3 degrees Celsius of warming, which the equivalent is 5.4 degrees Fahrenheit of warming, we would see the following. Arctic sea ice is gone 2 out of every 3 summers. 50% of insect species are gone due to habitat loss and climate change. Increases in average drought would increase by roughly 11 months. And if we look at the Mediterranean area here on our planet, summer wildfires would more than double. So these are really significant, but they are just a few. Let's take a look at some of the other impacts that we know are beginning to occur. So just last year, in July, we saw Phoenix and Miami both experience their hottest months ever. And if we look at Russia and we focus on Siberia, what we saw last year was that Siberia experienced temperatures above 100 degrees Fahrenheit. This was the first time that we ever saw temperatures of 100 degrees Fahrenheit this far north. And it was the first time that we ever saw temperatures of 100 degrees Fahrenheit in the Arctic. One additional thing that we're beginning to understand is a lot of this additional heating that occurs within our atmosphere is going directly into our blue oceans. What we see here is all this additional heat content that is going into those oceans. We see that rise over time, beginning right around or earlier than the year 2000, all the way up to today. And in fact, we set records in 2020. What we begin to understand, though, as it pertains to this heat content, is that most of that heat content is absorbed from the surface of our oceans to as deep as 300 meters deep. But what we've also learned is that that heat content absorption occurs much deeper than that. In fact, it occurs as deep as 2,000 meters deep and even further still. And unfortunately, over half of that increase has actually occurred in just the last 20 years. So what does that really mean in terms of catastrophic storms and weather events? So it certainly intensifies things like typhoons, cyclones, and hurricanes. And what we see here, if we focus on Hurricane Harvey, we look at the path it took over the Gulf of Mexico. When it did, the Gulf of Mexico was a full 7 degrees Fahrenheit hotter than average. And those temperatures of 7 degrees warmer went as deep as 200 meters deep. We see here storms like Hurricane Dorian, which was the strongest storm at landfall ever recorded in the Atlantic Ocean. When it struck the Bahamas, the winds were 185 miles per hour. We see storms like Hurricane Delta, Hurricane Delta went from a tropical depression to a full-fledged Category 4 hurricane in 36 hours. So imagine a storm going from a tropical depression to a full-fledged Category 4 hurricane in a day and a half. This is the first time a storm ever did this in recorded history, and this took place just last year in the fall timeframe. Now, what I want to do, if I could, is just illustrate for everyone an example of how these storms are increasing in terms of their frequency. And I want to use Hurricane Sandy as a great substitute or example to kind of showcase this. So Hurricane Sandy actually occurred over New York and New Jersey back in 2017. If we were to take a storm matching Sandy's magnitude and intensity, we put it back into the year 1880. A storm matching its magnitude and intensity would be a once in a 500-year event. Once again, that's a once in a 500-year occurrence. If we move it up to the time in which it actually occurred, which is 2017, it would be considered a once in a 25-year occurrence. But if we move this storm up, if we move Sandy and a storm matching its magnitude and intensity up to a future time period of 2030 to 2045, now a storm like this is a once in a 5-year occurrence. We now know also that there have been 20 1 in 1,000 year downpour events in the United States since May of 2010. And as a result, right, of all this additional water, all this additional rainfall, all of this additional heat content being absorbed into our oceans, we see much more evaporation from those oceans. And what we see here in this photo is all of that water vapor moving about the continents on our planet. So what does this really mean in terms of storms and weather events? So it transitions to much more global record-breaking precipitation anomalies. And we can see how these anomalies, these unusually heavy rainstorms, are growing over time exponentially. Globally, we see that floods and extreme rainfall events now occur 4 times more often than they did in 1980. And US farmers, right, these storms impact everyone in different ways. Back in 2019, US farmers were prevented from planting on 200 million acres, again, mainly due to these heavy rains and flooding events. Here's what we see is a great example of one of these flooding and extreme rainfall events. This took place in Ellicott City, Maryland, back in 2018.
Yeah, I don't think you're going to that wedding tonight, bro.
Let's talk about, though, something totally different. Let's switch from a conversation about all this additional water and talk about all this additional warming and the opposite effect. What we see here on this graph represented in orange, this is a graph of Europe where we see just last year where groundwater levels were alarmingly low. We really don't even have to kind of go across the pond or look across the ocean to see examples of these same things. We can see that here in our own United States. We now know that in our own US West, right, 70% of the West is experiencing extreme drought. And states like Utah, Arizona, New Mexico, and Nevada, these areas are particularly hard hit. Unfortunately, California, right, 93% of it currently is going through extreme drought. We also see in our US West Coast an ever increasing amount of forest fires. What we see here is as we get these increasing amounts and spikes in temperature, we can see a causal relationship in terms of the number of fire events that result from these spikes in temperature. And unfortunately, what we now know is that since 1972, the average area burned each year in the state of California has increased 500%. We can also see this in other countries. What I want to show you now is a photo of South America. This is a satellite photo. And what we see here, it depicts in areas of white, these are cities and towns. If we look at the orange areas depicted on the satellite photo area, this shows forest fires. And these forest fires are burning the Amazon rainforest. Now, they're set and created to make room for domestic livestock and agricultural products. But the Amazon rainforest is something that we refer to as a carbon sink. And it's a carbon sink because it acts to sequester, to absorb these additional carbon, these greenhouse gases out of our atmosphere. And it kind of holds them within the deep foliage, the leaves, the tree trunks, the soil itself. So when we actually cut down this forest, we inhibit its ability to support us in this way. But when we burn it, we do particular harm because we take all that sequestered carbon that's stored within those leaves and those tree trunks and that dense foliage, and we set it back up into the atmosphere. And we're now at a point where the Amazon rainforest is kind of at a tipping point, right? It could transition from being what we call this carbon sink into what we call a carbon emitter. And at that point, it actually does more harm than it does good because it puts into the atmosphere more carbon as opposed to what it takes out. We can see here a chart that represents extreme weather events. And this chart is done by the insurance companies themselves. It depicts here in orange, we see storms. In blue, we see floods and mudslides. And in red, we see extreme temperatures, droughts, and fires, and all the costs that are related to them. And in fact, in 2020, we set, according to the insurance companies' records, the costs associated worldwide with these catastrophic events roughly are $210 billion. What they also say in that same time frame is the actual insured amount of these extreme weather events was only $82 billion. So as you can imagine, people whose homes are burned, people whose homes are flooded, are having to deal with the worst of what climate change is bringing to bear, and they're having to do it without the financial support to kind of beat back the worst of what climate change will offer us. We now know, unfortunately, that here in the United States, $95 billion was created in terms of these climate-related damages just last year, just in 2020 alone. And unfortunately, we focus on this past decade. So from 2010 to 2019, these extreme weather events cost the United States over $1 trillion. This is a full 52% increase over previous decades. And we can see how the cost of these storms here in the United States has grown year over year over year. And in fact, we can see how that period from 2010 to 2019 is the largest time frame yet. So what kinds of things, as we talk about these damages, what pieces are most at risk? Predominantly, it's those building blocks of any community. It's the infrastructure. So things like sewage systems, bridges, roads, power lines, storm water systems, drinking water systems. These are the building blocks of any community. And these are the systems that are, in fact, most at risk. So I want to transition now. I want to talk about another impact of climate change. And I want to move to the polar regions of our planet. So here what we see is the Arctic. And we can see the sun's light and heat energy reflecting first back out into space. And that's a good thing. That's the way that glacial ice protects us from that additional warming. But what's beginning to happen is that glacial ice is beginning to melt. And as it does, all of that sun's heat energy is being directed into those blue oceans. So let's take a look at how that's beginning to impact, again, these polar regions. Here's a shot. This is a photo taken by NASA, a satellite photo. And it's, again, the shot of the South America and Antarctica. And it depicts here areas represented in blue, in red, and in purple, those areas on Antarctica, which are experiencing the highest degrees of melting. We can move back up to the North Pole and look at the Arctic. And what we see here over a time span of up to 1,500 years long, we see sea ice, glacial ice, melt and solidify. It melts and it solidifies, but it never truly changes that much. But what we see in the last couple of decades is how that glacial ice begins to melt and melt exponentially. If we move back down to the South Pole, we look at Antarctica. Again, we can see how there's ever increasing amounts of this glacial ice melting. And if we look at the period from 2009 to 2017, we lose roughly 245 billion metric tons of glacial ice. Let's transition yet again. Let's talk about one more impact of climate change, but let's stay and focus on those polar regions of our planet. So what we see here, I want us to focus on our jet stream. Our jet stream up to this point, as indicated in our photo, is really moving very rapidly. It's a very strong jet stream, and it moves very quickly across the northern hemisphere from west to east. Now what we're beginning to see, though, is something very, very different. That jet stream, as a result of that glacial ice melting, is beginning to wave a bit. It's beginning to weaken. And as it does, as I said, it begins to move in waves. And some of that polar air is able now to move over top of Canada and the United States. And oftentimes we hear this referred to in the news as polar vortex. So I want to give you an example of why this can be particularly concerning. What we see is a shot here of the North Pole, and we can see this jet stream moving kind of very erratically over top of Canada and the United States. And you can see it moves very slowly, and it moves within waves. And within these kind of troughs and ridges exist huge weather systems. These are things like droughts, floods, heat waves. And as it moves slowly, these storms and large systems are in fact able to stall, right? They're able to stall over large parts of the United States and Canada, and they can inflict large amounts of damage. We saw this in particular if we look at Hurricane Harvey, which dumped huge amounts of rainfall in Texas. We also saw this if we looked at Hurricane Dorian, which did huge amounts of damage to the Bahamas as a result of stalling over the Bahamas for long periods of time. And those hurricane force winds were able to do large amounts of damage. I want to show you, though, something that's very timely. This was that same jet stream. And this was this year, in January of this year. You can see it move very erratically, and in fact, it moves directly over top of the North Pole. As a result, what we saw, as many experts would predict, that we would see possible paralyzing cold polar air over the United States and Canada, and we could see these real extreme snowstorms. This is what we saw, sure enough, just 1 month later. Now this is that jet stream. That same jet stream moves and dips well over Texas. And sure enough, for the first time ever, the entire state of Texas was under an extreme winter storm warning. We can see here, as areas represented in blue and in purple, where these regions experience sub-zero degree temperatures. And in Texas specifically, their electrical grid failed, and many people were not able to heat their homes for almost up to a week. So let's transition again, and let's talk about all of those impacts of this glacial ice melting. One of the other important facts of this glacial ice melting is sea level rise. What we see here is top 10 cities most at risk from sea level rise by the time we get to 2070. And this graph, this chart, is done by population size most at risk. So we see here cities like Calcutta and Mumbai with populations of roughly 12 and 14 million people respectively, right? These cities have huge amounts of people that live there, right? And we also know these cities to be in parts of the world that we consider the developing world. So they may not have that kind of financial support to beat back the kind of worst of what climate change will inflict upon them. Now let's take a look at the same chart, but let's put it through a different filter. This is top 10 cities most at risk from sea level rise by 2070, but this is done by assets most at risk, right? Now we see cities in the United States jump to the top of the list. So Miami is number one, with assets most at risk surpassing $3.5 trillion. So these are the things that we talked about earlier, right? Buildings, roads, bridges, businesses. We also see New York and Newark jump to number 3 on this chart, with assets most at risk of over $2 trillion. Now, I want to give you an example. This is a mock-up, but it pretty much gives us a good idea of what we could see if we see as much as 3 degrees Celsius of warming and the kind of additional water that we could experience in many of our cities. Here's a depiction of Shanghai under 4 degrees Celsius of warming. This is London under those same conditions, a 4 degrees Celsius of warming. And this is our own Wall Street, right? This is the statue that kind of pays tribute to our financial markets. This, with 4 degrees Celsius of warming, is that same region. So there are a lot of impacts that we're beginning to see as a result of this glacial ice melting. Now, I want us to focus for a second, if we could, on a period that started last year to this year in February. This is just a 6-month time frame. So we're going to focus on a time frame from September of last year to February of this year. Globally, during that time frame, 10.3 million people were displaced. This is 4 times larger than any other extreme event we can ever call upon. So whether we're looking at war or anything else, this kind of displacement is unprecedented. As a result, you can imagine our government is very concerned about the impacts of climate change. What we see here is our own US Department of Defense has declared that climate change is going to or will likely lead to food and water shortages, pandemic disease, disputes over refugees and resources, and destruction by natural disasters in regions across our planet. And if we look at the tropics, which are home to roughly 3 billion people, if we see as little as 1.5 degrees Celsius of warming, many parts of the tropics could be considered unlivable due to an increase in heat and humidity. So I want to now quickly take a look at the areas throughout the planet that we already consider to be uninhabitable zones due to extra heat and humidity. And these are areas that consist or comprised of areas in Africa, in the Middle East. They exist in small fractional parts of India and Australia. But if we extrapolate this out, if we look at a future time period, right to 2070, now all of a sudden we see these uninhabitable zones grow exponentially. Now they're in parts of Central America, large parts of South America, Africa, the Middle East, India, the Pacific Islands, and even large parts of Australia. As I said, with areas like the Middle East, North Africa, possibly in a future time period being uninhabitable, right? There's going to be increasing pressures for these large populations to migrate. So once again, the question becomes, and we would have to put to everyone, where will all these people move to? Now, as a result of some of these significant changes, The Lancet, which is a publication that focuses on the health impacts of climate change, The Lancet has stated that climate change is the biggest global health threat of the 21st century. So let's take a look at why we think this would be. First, what we see here is tropical diseases are frankly on the move as a result of areas that are closest to the poles, the polar regions of our planet. As these warm up, diseases like West Nile virus, dengue fever, Zika virus are able to really take root for the first time. And no longer can we kind of rely upon these colder temperatures to beat them back as we could before. Additionally, we see the number of US tick-borne diseases cases have doubled actually from the time period of 2004 to 2016. And then mosquito-borne infectious diseases, right? They've increased 10 times here in the United States. Climate change has also increased the greater likelihood of waterborne infections. So things like cholera, dysentery, E. coli, these things are also more prevalent in a warmer climate. And then we can talk about ambient air pollution, right? Ambient air pollution is really important. So we know, and we've talked about the fact that as we add these greenhouse gases to our atmosphere, they do a lot of damage in terms of trapping additional heat. But these are also polluting gases, right? So in terms of death attributable to this ambient air pollution, here in the United States, they number somewhere between 5,000 and 20,000 deaths each year in the US. But if we take a look at China and other countries, China is a great example of kind of a worst case scenario because deaths attributable to ambient air pollution surpass 150,000 every single year. Even simple things like allergies are far worse in a warming climate. If we go back and we look at a period in 2000, grains of pollen per cubic meter were somewhere north of 8,000. But if we look at a future time period in 2040, grains of pollen per cubic meter will almost reach 22,000. Now, unfortunately, we're at a point where we believe we will risk losing up to 50% of all land-based species in this century. And this is due in part certainly to climate change, but also due to habitat loss. And as I transition, what I want to talk about is, as we talk about climate change, we often think about the fact that it's perhaps somebody else's concern. We look out west and we see forest fires, or we look out east and we see flooding as a result of sea level rise. But we think that this isn't a Michigan problem. And as I indicated at the top of our talk, it really is. We can see these same kind of changes here in our own state of Michigan. So I want to talk about that quickly. Here in Michigan, average annual temperatures have risen by 2 degrees Fahrenheit over the last 30 years. Now, heat wave days in Michigan are expected to jump from 15 days currently to nearly 42 days per year by 2050. By the time we get to the end of the century, 2100, summer temperatures in Ann Arbor will jump from 81 degrees to 93 degrees. Also, we can expect that future generations will see a very different climate than what we've experienced here in the state of Michigan for decades. Under the worst case emission scenarios, by the time we get to the end of the century, summer temperatures in the state of Michigan will more likely resemble those in the state of Arkansas. We can also expect in and around our own Huron River watershed to see warmer than average temperatures, more extreme nighttime temperatures, more potential for overall extreme heat, shorter winters, more total precipitation, and more of these extreme precipitation events. It's these extreme precipitation events that will do the most damage. This extreme rain and flooding, these will be the most significant here in the state of Michigan. We can see here over the course of an entire century how rainfall has increased here in southeastern Michigan. And we can see here how we've seen an extreme amount of declining Great Lakes sea ice cover. In the period from 1973 to 2010, we saw a reduction of 71% in terms of Great Lakes ice cover. Now, at this point, Lake Superior is warming twice as fast as nearby air. And we can also kind of expect that by the time we get to mid-century, Lake Superior will see little to no ice cover in a typical winter. As I said again at the beginning of our conversation, winter's beginning to change. So winter precipitation is truly beginning to evolve over the years. We're seeing shorter winters have led to more precipitation, and that's falling as rain instead of snow. We're seeing warmer surface temperatures have reduced overall snow accumulation. We are beginning to see kind of more of these extreme precipitation events brought on by lake effect events. But these events oftentimes will end up bringing us more precipitation as rain as opposed to snow, because again, temperatures are warming here in our state. We also see fruit crops being extremely impacted. If we look at what's happening in our winters, we're seeing winter temperatures toward the tail end of winter kind of warm up abruptly. And then as a result, these fruit crops begin to bloom. Then what we see following that is these corresponding cold snaps. These cold snaps are very normal for that time of year, but they kind of increase the likelihood of doing extreme damage to these fruit crops. Back in 2012, we saw $92 million in damage to the tart cherry crop here in Lower Michigan. We also see the damages of these cascading impacts from algae blooms. So what we see here is stronger storms, more agricultural and industrial runoff. This creates greater nutrient loading that goes directly into our warmer lakes. We're seeing that the lakes and the dynamics of these lakes change over time, and they're less stratified in terms of temperature. They're warmer overall. And as a result, we see greater algae blooms. And as a result of also this stratification, we experience these layers that are void of oxygen, and we create these huge fish die-offs. In addition to that, clearly algae creates conditions such that these lakes become not safe for drinking or for swimming. And then finally, we can see here changes to our ecosystem here in the state of Michigan. If we were to look back at a period of 1960 to 1990, and we look at our map on the left, what we see is most of the foliage really was comprised of maple, beech, and birch and aspen trees. But if we jump to a future time period, right, 2070 to the end of the century, most of that foliage transitions to oak and hickory. And it's because these kinds of foliage will be the kind that will be able to sustain itself in a changing climate. So now let's take a look at all these various impacts. And we're going to put them into what I call our cost of carbon cash register, because they all are expenses and they all create costs to our economical system. So right here we are, and we can see each of these examples of costs of carbon, right? I've covered most of these, but there are several really that I've begun to, or I've almost not really begun to scratch the surface of. So things like ocean acidification, political instability, famine, water scarcity, these are also costs of carbon. So in this case, what ends up being the biggest cost of carbon is its threat to our global economy. So now I want to put that question that I put to everybody at the beginning of our conversation. Must we change? Right? The answer is definitely. We need to do things different. So let's take a look at that next question that we talked about. Can we change? And the answer is we can, right? We have the solutions at hand. We can transition. We have the techniques, the skill to do this. What we lack a lot of times is the will, particularly the political will. So let's talk about some of these positive technologies, because they really are exciting in terms of our battle against climate change. First of all, let's focus on wind energy. So wind energy, as of the year 2000, it was projected that worldwide wind capacity would reach 30 gigawatts by the year 2010. In fact, the reality was by the time we get to 2020, we surpassed that by 24 times. Now we can see all the exponential growth of wind capacity or wind projects that we're adding here in the United States. From a period of 2001 to present, we can see how we're growing this technology exponentially. Why is that important? It's particularly important because globally, wind could supply global or worldwide electricity consumption 40 times over. Now let's focus on solar energy, because this and its prospects are even greater. So in 2002, prospects were that solar energy, that market would grow by 1 gigawatt per year by 2010. In reality, we grew by 2010, we grew that market by 17 times. And by the time we get to 2020, we grow that market by a full 132 times. We can see the ever-growing amount of solar capacity that we're adding. What we see here is exponentially. In the United States, we're adding solar projects or solar capacity. If we look at the year 2000, it's almost non-existent, but look at how that has kind of transitioned and grown as we see it today in 2020. Why is that really relevant, right? One of the things for all of these technologies is that they need to be viable, and to be viable, they need to decrease in cost. Whether we're focused on computers and laptops, whether we're focused on cell phone technologies, all of these technologies to be viable have to reduce in cost. If we look at solar technology and we look back long ago, say in the 70s, a watt of solar energy would have cost us roughly $80. But if we move to a time frame to today, so 2020, a watt of energy from solar power would cost you just 20 cents a watt. right? This is a significant change. And these technologies are even growing and getting better and more efficient. Here's a great example of a profound success story. If we look at South America and the Chilean solar market, we can see that as of 2018, they saw great success. But if we look at 2018 to the present, they grow their amount of solar projects exponentially. And they do this because they, as a government, they incentivize it. And then as a result of that, right, Chile adds an additional 16.67 gigawatts of solar projects either approved or under construction. Why does that become important? It's critical because there's enough solar energy that reaches the earth every hour to fill all of the world's energy needs for a full year. One of the other technologies that I want to talk about and introduce is solar capacity, right? So battery storage. This is particularly important as we start talking about these sustainable energy forms like wind and solar, because we need something to store that energy when the wind isn't blowing and the sun isn't shining. What we see here is storage capacity is growing over time. And if we extrapolate this growth out all the way to 2040, we can see that we can expect storage capacity or storage products or projects to grow globally all the way through 2040. Simple things, even simple things like LED light bulbs are growing in their usage. If we look back to the incandescent light bulb, which was extremely inefficient, LED light bulbs have really taken hold. And by the time we get to 2025, they will comprise of roughly 95% of the overall market. If we look at automobiles and automobile manufacturers, here's a list of all those manufacturers that are currently producing electric vehicles or are in talks to do just that. And as it pertains to batteries, right, that technology is particularly important when we're talking about electric vehicles. We now, in fact, know and can see that General Motors has announced it's phasing out all of its gasoline and diesel-powered passenger vehicles by 2035. And that global electric vehicle market is growing exponentially. We can see here now it surpasses 9 million vehicles worldwide. That includes both full EVs or some sort of plug-in, some hybrid EV. So let's ask that second question again. Can we change, right? The answer is yes. We can definitely change. As we kind of wrap this up, let's ask that final question. Will we change? And there are a lot of good indicators that we will. Let's talk about some of those positive indicators. Let's first focus on the Paris Climate Accord or the Paris Climate Agreement. This was talked about back in 2015. It was an agreement whereby every nation in the world agreed to work together to achieve net zero greenhouse gas emissions by the time we got to mid-century. Now, we were poised to get out of this agreement. And as a result of our new political administration, we're back in this agreement. This is particularly important. We want to lead on this front, and we certainly want to export these kind of sustainable energy technologies to the rest of the world, because that's simply good for business. Here's yet another example, a positive example of a change that we're beginning to see. If we look at this graph, what we see here is the positive impact or positive trend line of our S&P 500 following the Great Recession of 2008. If we were to layer on top of this the Dow Jones Index and its performance, we would see the same kind of exponential growth. But if we take a look at the growth or lack thereof of conventional energy stocks, so gas, oil, and coal, during the same time frame, this is the performance that we see, right? This is important because what we're beginning to see and investors are beginning to understand is that gas, oil, and coal are not the energy forms of the future, right? It's sustainable energy forms or sustainable forms of energy, which will actually be used. Things like wind and solar will be the predominant forms of energy going forward. What we also know is that gas, oil, and coal producers over time may simply have to take those deposits, right, that live within the ground and write them off their balance sheets because it will be more expensive to extract them as compared to the sustainable forms of energy that we get from wind and solar. We also know now that investments in renewables and energy efficiency create 3 times more jobs on average than these investments in these old fossil fuel technologies. Finally, one other myth that we have begun to bust. If we look at this chart, what we see is our GDP and how it's grown exponentially since the year 1950, right? One of the things that we thought as a country is, as a country that depended so intrinsically on fossil fuels, if we were going to succeed, if our gross domestic product was going to continue to grow, we would have to expect that a byproduct of that was to see emissions grow alongside it. The truth is these two are being decoupled. What we see now is CO2 emissions are beginning to become flat, and yet our economy is still beginning to grow. This is because we are able to add sustainable forms of energy like wind and solar more quickly. It's also because we raise our benchmarks. And a great example would be the emission standards that we put on automobiles. But other technologies also reduce the amount of carbon that we put into the air. So we see again that myth busted, that in order for our country to do well financially, that CO2 emissions have to rise in kind. We see a global transition in terms of energy dollars being transitioned into sustainable forms of energy. And we see how quickly this is beginning to occur. So if we look at a period in 2014, electricity from wind and solar was cheaper than new coal and gas plants in approximately 1% of our world. By 2019, just 5 years in advance of that, right? Solar and wind energy are the cheapest forms of new electricity in 2/3 of the world. But if we jump to 3 years from today, now wind and solar become the cheapest forms of energy globally. We now know that between 2014 and 2019, US solar jobs grew 5 times faster than the overall economy. And we see here, if we look at the global building efficiency market, right? This is a market that's huge, $300 billion. This is that market that takes shape. If we improve the efficiency of our buildings by adding additional or changing the windows and doors, the types of insulation, the types of heating and cooling systems that we use, think of all the jobs that we could create by improving the global efficiency of our buildings. We also know that over 290 global companies have made a commitment to go 100% renewable in terms of their electricity. These are all the logos of but a few of those companies. Here, what we see is the United Kingdom, the European Union, Japan, South Korea have all set aggressive emission targets, right, to be net zero carbon emissions by 2050. And China has agreed to do the same by the time we get to 2060. We also know that more than 70% of the US voters support requiring 100% of electricity in their state to come from wind and solar by the time we get to 2050. Finally, here's another great byproduct that we see from changing and transitioning to clean sources of energy. Health benefits from wind and solar power in the United States from 2007 to 2015 were actually greater than their climate benefits. So imagine the climate benefits that we recognize, those benefits that we incur from damages that we don't recognize, amounted to $32 billion. But if we look at their corresponding health benefits during the same time frame, that's $56 billion. So why do we think that that would actually occur? Well, these are but a few examples, right? We see a decrease in the amount of premature deaths resulting from air pollution from fossil fuels. We also see a lessened amount of emergency room visits resulting from asthmatic conditions in adults and children. We also see things like lost work hours, right? These have a cost to them too. As a result of reducing all these various costs, they have a profound reduction in overall health costs. We see here US cities that are committed to going 100% renewable in terms of their electricity. We also see cities throughout the US that have already achieved this. And then finally, we see here in our own state of Michigan, these are all the cities that agreed to achieve the result of net zero carbon emissions by a particular date. Washtenaw County has agreed to achieve this by 2035. Ann Arbor, its goal is set for 2030, and Grand Rapids is set for 2025. Finally, what we also see is more people speaking out, expressing their concerns about climate. Here, what we see is the People's Climate March in Washington, D.C., right back in 2017. People are really beginning to tell their legislators that climate change is important. And here, what we see back in 2019, in 185 countries, over 7 million people spoke out in the global climate strike. But actually, we can see that locally. Here's that same climate strike on the DIAG on the U of M campus back in 2019. So as I kind of wrap this up, I want to talk about the fact that it's really important that we kind of do what we can do as individuals kind of to make the biggest impact that we can make on climate change. So let's talk quickly about what the things are that we can do to make the strongest impact. So first off, our voices. It's important that we use our voices. When it comes to climate change, talk to your friends, talk to your neighbors, talk to your coworkers. Certainly reach out to your legislators, whether those people are the people in Washington, D.C., or our legislators locally here in the state of Michigan. Make your voices be heard. Let those people know that climate change is important to you. The second and also vital, important thing in terms of what we can do individually is use our votes, right? Use our votes to make a difference. We want to make sure that if we see climate change on the ballot, that we lean into it. We understand it, right? What's being written? Does this really do what we want it to do? So understand it first and foremost. And then if it does what we hope, vote for it. Secondly, vote people into office, right? That really are strong advocates of climate change. We want to make sure that we put the people in place who will vote for policies that are important to a warming climate. Finally, choices, right? Our choices in the marketplace really can play a very important role. So think about the choices that you make, the brands that you shop for every day. If I have, as an example, a vehicle that I buy year over year, there's a manufacturer that I support, and I say to that manufacturer, you know, I'd like to continue to buy a vehicle from you. But for me to do that, you need to be able to offer me an electric vehicle, right? We can make a difference in terms of the habits of organizations and corporations. What we do as customers makes a profound difference to them, and they listen to us. So do your best to kind of fight for the future, the community, the actual world that we want to achieve. Organizations, right? There are a lot of organizations locally that can make a big difference. Reaching out to these organizations can help you understand climate change a little bit better. They do a really strong job of information, providing more information on climate, but they also can help you understand how to get involved here locally if you're so inclined to do so. I'm a member of Climate Reality Project, and we actually are doing a kind of a climate training in October. This is going to occur digitally, and this is a great tool to kind of get a firmer hold on climate change and to understand, again, if you're so inclined, how to get involved. So finally, I just want to reiterate as I close this conversation, I want to thank you for your time, but I want to urge you to do what you can do. Use your voices, your votes, your choices, speak truth to power like your world depends on it. Because when we're talking about climate change, the fact is your world does depend on it. So once again, I thank you for your time and greatly appreciate being able to speak here at the library. Thank you.